And welcome to 4.6. I'm Gregory Carlson. This is the actual last section of Chapter 4. I think I might have said 4.5 was the last section. So what happens if something is continuously compounding? Your bank account compounds once a month. What if something is compounding continuously? Well, then the formula is a little bit different, and it's actually easier than the compound interest formula. Here's what it is. A equals P. Right? So far that seems familiar. It looks like the compound interest formula. But then instead of 1 plus and so on, it's just E RT. So A equals P times E to the RT is the continuously compounding formula. So what are some real life examples of stuff that's continuously compounding? So examples include, like say you get infected with a virus of some kind. Well, unlike your bank account, which only compounds once a month, the virus is infecting your cells and dividing all the time. And as a result, it's continuously compounding. And another example would be population. That people are having kids all the time, and so that's something that is continuously compounding. So let's look at an example. A population grows at a rate of y equals 2e to the 0.04x. How long will it take for the population to double? Well, look at this. And look at this. Do you see how they're kind of similar? Based on that, what is our current population? It's our principal. In this case, the current population is 2. So the question is, how long will it take for the population to double? So here's how you solve it. Instead of a y, we write 4. Like that. Notice that the rate is kind of 4%, continuously compounding. But you just, if it's asking us to double, you just take your current population and double it, and that puts the 4 right there. So now we'll divide by 2. And we get 2 equals e to the 0.04x. So here's something I want you to notice. What if this number had been a 4? Then we would have doubled it, right, and had an 8 there. And then when you divide 8 divided by 4, we'd get a 2 again. What that means is that the amount of time it's going to take for the population to double, if it's compounding continuously, that time is independent of how big the population currently is. In other words, the time it takes to go from 100 to 200 is going to be the same as the time it takes to go from 1,000 to 2,000, or 15,000 to 30,000. And so it's doubling at a constant rate, I guess you could say. All right, so let's solve this. The only thing we can do here is take the natural log of both sides of the equation. So we get the natural log of 2 equals the natural log of e to the 0.04x. So let's go ahead and take the natural log of 2, which is 0.6931. And on the other side, we have the natural log and the e. Again, we took natural logs so that we could get this down. And the natural log and the e undo each other. And they don't really cancel. They undo each other because they're inverses of each other. So if you have the natural log of e, they undo each other, and you're just left with 0.04x. One step away, divide by 0.04. So I'm going to keep this number in here so that my answer is more accurate. Divide by 4. Nope. Try again. Natural log of 2 divided by 0.04. How about? Natural log of 2 divided by 0.04 is equal to, and you get an answer of approximately, I should use an approximate symbol here, approximately equal to 17.3 years. So if we're growing at a rate of 4% continuously, then we're going to double about every 17.3 years. Another example of continuous compounding is radioactive decay, except that this time the compounding is negative, so you get less and less radioactive material over time. If 16 grams of a radioactive substance are present initially, and 3 years later only 8 grams remain, then how much of the substance will be present after 4 years? So it's important to understand that for linear decay, we can't just use the midpoint formula or the distance formula, because radioactive decay doesn't do this. It's not linear. It does this. Okay? It's a natural log. It curves down. If we were to put these together, it's more like it does this. So we can't just use a distance formula or midpoint formula. We need to go ahead and set up the log. And so here's how he would do it. The formula is A is equal to P e to the RT. And let's plug in what we know. We know that initially we had 16, and we dropped down to 8, and that took 4 years. I'm sorry, 3 years. And this is really good because now we can figure out what the R is to make this possible. Okay, and then we'll be able to solve for 4. So let's find this R. Let's start by dividing by 16. And we get a half. I'm going to write it as 0.5 is equal to e to the 3r. And this half shouldn't be a surprise because it's a half-life. So let's take the natural log of both sides. We're going to get the natural log of 0.5, which is equal to negative 0.6931. And when we take the natural log of e to the 3r, the e and the natural log undo each other, giving us just 3r. Then divide by 3, divide by 3. So r is equal to, maybe I can get the calculator this time, negative 0.231. So that's not our answer. That's just the rate for which produces this half-life. So our updated formula is A equals P e to the negative 2.231 t. So here's our updated formula. So now they want to know how much is left after 4 years. So all we need to do is just plug in a 4 right there. So it's 16. Sorry, I put in my principal. We don't know how much we're left with. That's the unknown we're going to try to solve. And so our initial amount was 16. E to the negative 0.231 times 4. So we plug in a 4 here, a 16 here, and we want to find out how much we have left after 4 years. If you think about this as in terms of an XY equation, the Y is the amount of material left, and the X is time. And every time is going to give you a different material amount. So let's solve that. Let's do that. This number times 4. And so we're going to get that the answer is 16 times e to the negative 0.924. So, and let's add a 2 in there just to be a little bit more accurate. So let's do, oh, I could have just hit the E button there, I think. That's okay. Let's oops, that should be a 1. Let's do that again. 0.231 times 4 equals, throw the negative sign on it. And if I do this, I believe it takes e to that number, which is equal to 16 times 0.3969, and then times 16. So it's going to be 6.351, approximately, grams. That's the amount of material. So we started with 16. After 3 years, we had 8. After 4 years, it would be a little bit less, about 6.351 grams. Let's do this last one and wrap up this video. Sorry, bumped my camera. An Egyptian mummy is, oh, this is really cool. So this is how carbon dating works. So here's how it works. When you eat food, most of the carbon in your body, like 99%, is carbon-12. But a little bit, about 1%, is carbon-14. So you actually have a little bit of radioactivity in your body. Now, as you keep eating, you keep taking in more and more carbon. But when you die, you stop eating carbon. So the remaining carbon in your body stops getting replaced, the carbon-14, and it starts to decay. And since we know the half-life of that decay, we can work backwards to find out when the Egyptian mummy stopped eating or how long it's been since that carbon-14's been in their body, how old that Egyptian mummy is, or anything else that takes in carbon. So that's pretty cool. So an Egyptian mummy is discovered in which the amount of carbon-14 present is only 1/3 the amount found in living human beings. Here's the formula. This is for carbon 14, and we would have done experiments to figure out this number. About how long ago did the Egyptian die? So we know that it only has about 1/3 the amount as it did initially. So what would we plug in for y and y original? Why not? It would be 1 equals 3. Because originally it had 3 times the amount as it does now. I hope that makes sense. So it only has 1/3 the amount. So initially it would have had 3, whatever 3 is, and we put a 1 there. Or you can put in any pair of numbers, but the point is when you divide, you want to get 1/3. So we could have put 9 and 3, or 3 and 1, but as long as you get 1/3, it doesn't really matter. So this is the equation we want to solve. If this is the rate at which carbon-14 continuously decays, how long did this take? So let's take the natural log of both sides. There's 1/3. Take the natural log of it, and you get negative 1.0986. On the left, the natural log and the e undo each other. And you get this equation. And now we're one step away. Just divide by this. Oops, don't divide by the t. That would be bad. And then we just do that and we get our answer. So we'll take this number. I'll leave it in the calculator. Divided by 1. Oh, darn it. I messed up. Stop it. Let's do 1 divided by 3. Natural log is this number. Divided by, I hope you take solace when I mess up. Everybody makes mistakes. 0, 0, 0, 1, 2, 1, 6, and I'll even throw the negative sign on there. We know that the final answer is going to be positive. So according to our carbon dating, it took 9,034, approximately, of course, 9,034.6 years for that amount of carbon to 14 to decay. So there's a lot of interesting applications of continuous compounding things, including carbon dating. So hopefully that made sense to you, and I will see you for a few more examples in part 2. See you there.